Assalamualaikum warahmatullahi wabarakatuh. Let me introduce myself. My name is Addino Dimas with the NPM of 1906356916. And today I would like to present about the gate valve simulation with CFD-SOF. So what I would actually share is the steps on how to use the CFD-SOF, especially in optimizing the gate valve. The steps actually consist of three, but the first one that I would like to share first is the CFD3, which is we open and import the previous installed the get file first. Then after that, we look over the generate section to set up the surface refinement maximum level. So we fill up the maximum level of 2. We also fill up the layer mesh section. The number of layers, we fill up the number of 5 with the expansion ratio of 1.25 and the first layer thickness of 0.2. And then after that, we beneath the base mesh box, we set the valve diameter to 1 inch in the box mesh dimensions. So after that, we also fill up the box mesh properties with the division of 10 each one, and then also with the same amount of grading portion, which is 1. Then we examine the boundaries of the X, Y, and Z axis. So yeah, and then we identify the name of the inlet and outlet. So the X minus X, we would put it as an inlet, and then X plus is the outlet. The Y minus is the boundary. Y plus face is the wall. Z minus face is boundary, and Z plus face is boundary. And then we decide the mesh location in X, Y, and Z axis. We choose the yellow on the inside of the valve to generate a less smooth mesh. And then we use the surface refinement to smooth the mesh with a maximum value limit of 3. Sorry, this was a typo. So yeah, after we generate, the program will produce this result of generation. Then the second step is the CFD-SOF that we do, which is the simulation model, which is a part of the 8th step. We determine the turbulence conditions, the fluid properties, and the boundary conditions. So first of all, this is the simulation model. We will fill up the box mesh dimensions with the minimum coordinate of 0.011 in meters and the maximum coordinate of 0.047 in meters. We fill up the box mesh properties, the box mesh boundaries as well, like we did before. Then we will determine the turbulence conditions first. In Reynolds average Navier-Stokes or Rance method, we would determine the turbulence model as K omega as a default coefficient. Yeah, this is the turbulence model coefficients we get to see right here with the various numbers. And then the materials, the fluid properties, I use an air as the material with the density of 1.225 kilogram per meter cube, and then dynamic viscosity of 1.79 pangkat 5, yeah, etc. So we will determine the boundary conditions. After that, the phase name of the boundary properties is the inlet one, the phase type of patch, and the condition type is velocity inlet. We will use the reference value of 8 meter per second of velocity, and the pressure type is zero gradient. And then also for the outlet one, the boundary conditions type is outflow with the velocity type of zero gradient, and the pressure type is fixed value of 0 meter quadrat per second quadrat. Then the ninth step is fill in the amount of iteration of 3,000 times. So yeah, we start from the start time of the time control and the amount of iterations of 3,000. And then we get to continue on the data control. The write control is iterations with the write interval of 3,000. And then the parallel control, the parallel run control mode is serial. So this is the result of a residual graph. In this graph, you can see the comparison between time in second and also momentum in residues. So yeah, in the 763rd iteration, the convergent solution starts to be able to be examined. So let alone 3,000, we actually get to see the result in this 763 iterations. And then the last step is CFD pause. But in this last one, we use the ParaView software. So we will open this one first. And then we multiply the pressure by density to find static pressure. Then the static pressure will become kinematic. So yeah, this is the pipeline browser. We would name it as like this. But the result array name is P static or pressure static with the formula of P times by 1.225. The result array is magnitude of U. And then we would find the result array name of dynamic pressure with this formulation. And then the array name of total pressure, which is the equation, which is the static pressure plus dynamic pressure. So yeah, after that, this is the inlet, outlet, and area result. So we will see right here, this is the points magnitude, the coefficient, etc. for each component. Then the last one, we subtract the total inlet pressure and the total outlet pressure to get the pressure drop. So yeah, this is actually the point of gate valve simulation, that we want to gain the pressure drop. But the final calculation we do right here is using the Microsoft Excel, where we would gather this data of velocity, area, P inlet or P outlet. So as we already determined before, the velocity is 8 meter per second. The area is 0.0002 meter square, and then the inlet pressure is 0.0635 Pascal. The outlet pressure is 0.0168 Pascal. So yeah, the equation of or the formula of drop pressure drop is uh, inlet pressure subtract to outlet pressure, which is gain as 0.046687 Pascal, and the debit is area times by velocity, which is 0.001728 meter cube per second. So that's all for me. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.